sorry, we will go to another paper. Preparation. This paper is about an investigation into fiber irregularities with
Thank you for that. My name is Chris Haren. I'm actually presenting this paper on behalf of Professor Zhonggai Wang, Wendy He and Li Jing Wang. Unfortunately, they weren't able to come, so I'll work my way through it. Unfortunately, it's not in my field. I've had a bit of a talk with a few people, so I won't be able to answer many questions, unfortunately, but I'll take some names and so forth and get some English comments back. The aim of the study was to summarise the ongoing work that's happening at Deakin, and also to look at research work into fibre behaviour with regards to strength. Most of the strength work and so forth that's been done on fibres has been done on uniform or theoretical fibres that are even in diameter over the length. So our work is looking at the fibre actually being like a natural fibre where it doesn't have even diameter along the length of the fibre. Why are we doing it? Natural fibres aren't even. You look at any of your fibres such as wool, cotton, hemp, rami, kanath, any of those fibres, as you go along the length of the fibre, you get diameter variation or width variation. Most of the theoretical study is on these cylindrical, uniform natured fibres. This slide here is an example of the diameter variation along the fibre. It's an output from single fibre analysis or CIFAN. It was a merino wool fibre that was measured here of about 25.2 micron diameter. The measurement intervals were every 14 micron. Sorry, I should explain it. You'll see as you travel along the graph that the fibre diameter varies between about 21 right up to about 32 micron. So research finding one was looking into mechanical fibre properties. And this work was started by Dr. Li Jing Wang, and then the theoretical side of it was continued by Professor Zhonggai Wang. What we've got, you'll see the first part of this, I'll just see if this pointer will work for me. You'll see this is the CV, the coefficient of variation of the braking load. The pointer doesn't want to work for me. Yeah. The other is the CV of the minimum fibre diameter. And what we did was we looked at the relationship of the minimum fibre diameter, the CV minimum fibre diameter on braking load. We come up with two equations. One of the equations is a more accurate version of the other, but we found that the lower equations work for most situations. And verification of research finding one, you'll see what we did was we measured 40 fibres using the CIFAN system. Each fibre was scanned on the CIFAN system for diameter, and we worked out the coefficient of variation of the minimum. You close? So each fibre was measured by the CIFAN. We calculated the minimum, the CV of minimum fibre diameter. A prediction was made from this, and you can see the two predictions are two lower predictions. One was the more accurate, the other one was just the quick formulation. The strength was measured on each of these fibres, which is our top CV percent measured, and we were able to look and see how close they were. And you can see that the relationship there is fairly close. second research finding that we have is the work of Wang, and it's mainly to do with breaking strain. Due to the thin spots in the fibre stretching more than what the thick spots do, you have a change in strain when you have these smaller diameter portions in a fibre. So the more smaller diameter portions you have in a fibre, the higher the strain. You'll see we have E max, which is the maximum strain, E average, which is the average fibre strain, and CV of CVDA, which is the CV coefficient of variation along fibre diameter variation. So tensile tests only measure the average strain. So we believe we were the first to have a look at this actual formula, and the first to get a verification on. This is verification on this fibre. We took the work of previous research results of Bankley and Slam, which they conducted on 5 fibres. They took each of these individual fibres and they marked sections on them over unit lengths. They then measured the extension of these fibres for their length. They put a uniform strain on them. You'll see 5.2, 15.5, 24.2, 32.9 and 30.9% strain onto these fibres, and they measured each section to see how much each section had grown in length. As you can see, we have the calculated results, which is the black. That's our results from the formulation that I showed you on the previous page. And you have the white section, which is the work from Blinkley and Sen, and you'll see that it relates very, very closely. What we did was we then went and proved it further with further work at Deakin University, which I haven't got on the slide here. Research finding 3, once again the work at Zhang. Now I've got no idea what the Weibull distribution is. All I can say with this is it's a fairly well-known equation which was developed by Weibull back in 1951. It has applications with regards to strength, failure probability based on the weakest link theory. In the original formulation, the lambda wasn't actually in the formulation. So this is the correction factor that we put into the Weibull formulation to make it true for natural fibres. And what it means is the longer the fibre, the greater the chance of flaws in the fibre. And hence the longer the fibre, the less strength that you'll have. The original equation does not have a geometric factor in there. The parameter greatly increases the accuracy of the equation. So once again, we have verification of this. You'll see the white column is the experimental, the Weibull calculation. The hashed column is our estimation using the new formulation of the Weibull system, and the black column is the actual experimental data. So you can see over the range of a standard fibre, which is 10 to 100 millimetres, pretty much cleans up every fibre there is in regards to natural fibres. The equation holds true far better than what the original equation does. Now this is all the work that I've shown previously is work that's been completed. This is now the ongoing work that we're doing, and this is ongoing work under the Wang with regards to modelling, computer modelling of fibres. So you can see here we have 2 fibres that have been modelled. One's a cross section of the top fibre, and this is just a an average idea of what a wool fibre would look like. It has these lumps and bumps and that sort of thing. It uses a Cartesian coordinate geometry system to model this fibre. So we've got several different forms of irregularity you can have in fibre. You can have variation in diameter, and you'll see this is a cross-section of the fibre. We have 10% variation, 30% variation, 50% variation. We also have the effect of frequency. So you've got fibre diameter variation, you've got fibre frequency variation. The modelling looks at several different frequencies. You can see 1, 2 and 3 in this fibre, but the computer modelling will handle far more than that. Then she looked at the effect of buckling behaviour because of these fibres. Now once again, most of the work that's been conducted is looking at a perfectly cylindrical fibre. So when you get a fibre that's not perfectly cylindrical, it starts to behave totally differently in buckling. Now this has great ramifications with regards to comfort factors, because depending on what diameter fibre you have hanging out of a piece of yarn can increase or decrease the scratch or the prickle coefficient of the fabric. Another area where you get this occurring is in the shearing effect for wool fibres. Shearing as in the clipping of the wool from the sheep. You'll see that depending on whether it's got a fine tip or a coarse tip, this can, and when you shear, can greatly affect what the fibre is going to look like. For example, in summer when the food is very lean and so forth, the fibre of a sheep tends to lean down in diameter, and during spring when the animal's on very good feed, it tends to grow in diameter. So it's very important that when you're shearing. So conclusions on this work is the level of diameter variation significantly influences the tensile behaviour of a fibre. Fibre diameter variations can be used to predict the variations in fibre breaking load and the maximum tensile strain along an irregular fibre. Numerical modelling can reveal the effects of various irregular attributes, level, frequency, etc. on the fibre mechanical behaviour. That's all I have. I'll try and take some questions. I may need to take them down and get an answer for you at a later stage. So, thank you. Thanks, I'm glad you didn't ask any questions.